Okay, so looking at conservation of linear momentum is kind of like what we talked about before, like conservation of energy or mechanical energy, as long as you don't have stuff that escapes. And so that's kind of the same thing, and that's what this section is talking about. And it goes kind of, in my brain, a long roundabout way of explaining it. But essentially, the idea is if you're looking at a problem, you can either, for example, solve the problem for one, and then the external force is the blue thing, or not the blue thing, but the, you know, what I mean, hold on. That's actually a velocity, so that's not a good example, or a good way of me saying it. So like say number one hits number two. So if I do just a free body diagram of one, then two hitting it, that's the external force that goes here, right? If I do just two, then one hitting two is just that force hitting it. Okay, so if I'm doing these in two separate universes, linear momentum is not fully conserved because there's an external force hitting on it. Okay, however, if I do 1 and 2 and I do this system, then there is no internal forces and there is no that thingy, sort of. So like this would be like MV1, I don't know, initial, I'll just call it MV1 plus this FDT, except I didn't put that on the right thing. MV11 plus FDT equals M velocity of the first one final. And then over here it'd be like velocity of the second one initial plus, except now the force would say be going the opposite direction, FDT equals mass velocity of the second one final. And if the masses are different, you know, you could have m sub 1, m sub 2. Or, so you can either have that first equation and the second equation, and then sometimes, if you want, you can write the third equation, which is the mass of the first one times the velocity of the first one, plus the mass of the second one times the velocity of the second one. And then there's no impulse, because everything's contained, then that equals mass 1 velocity 1 final plus mass 2 velocity 2 final. Does that kind of make sense? So basically the idea is, depending on kind of what you're drawing your circle around, if there's any external forces, then those need to be represented here. And if you're in the same system, it's going to be positive on one side and negative, or positive in one of the equations and then negative on the other one of the equations. But if you look at the system together of things that are colliding, then as long as there's no deformation, so let's assume no deformation, like the you know, like when the balls hit each other, they're not actually, you know, changing shape, then there's no impulse. Okay, sort of, it's kind of weird, and that's really what this is saying, and I don't know why it's telling you all of these things. So yeah, the mass of the system has to remain constant. So, you know, if the cue balls or pool balls are like emitting flames and bursting into flames while they're, then that doesn't work. So yeah, the net external force must be 0. We just said that. So conservation of momentum. So that's what this is talking about here. Doop-de-doop-de-doo. All right, let's see if we can do this problem. Okay, so 2 carts in a lab, roll. The carts have magnets so that when they collide, they stick together. Okay, that's important. The first cart, I'm going to call this cart A. First cart has a mass of something and is rolling to the right. So 675 grams. 0.6 675 kilograms, and it's going 0.75 meters per second. And then you have B has 0.5 kilograms and is also rolling to the right. Oh, I thought they were going to be rolling toward each other. Well, good thing I read the problem. After the collision, what is the velocity of the two joined carts? Okay, so if I'm looking at as a system, okay, it doesn't matter what the force is between them because they're stuck together, there's no deformation, and I'll show you what this is doing. Okay, so basically, we're going to start off with, so the mass of, so hold on, let me write it in words first and see if that helps. So we have initial momentum of A plus the initial momentum of B equals the final, final momentum of the A plus B combo car. I don't know if that's helpful. Okay, so the initial momentum of A is 75 or 0.675, yeah, 0.675 kilograms, and this is all going to be, so I can do kind of like the linear conservation in the x direction if you want to write it like that, like if you kind of want to do it like we were doing the forces, I sometimes will do it like that, like what's the sum of the linear momentum in the x direction? I use L because I'm lazy, but you know, you can use P or whatever makes you happy, times 0.75. I just want to make sure you know that this is going, because I'm dropping my vector notation, I'm just going to say it goes in the positive x direction. So 0.675 times 0.75 plus the momentum of the second dude is 0.5 times 1.33, and I don't know their final velocity. So wait, this is kg meters per second. Kg meters per second. Okay, the final combo has a kg of the two of them together, and then I don't know what the velocity is. Okay, maybe? So it's really like, the math isn't that bad, it's the concept. And please resist the temptation to be like, I'm just gonna like not learn anything and plug stuff in and hope nobody notices. It's a terrible idea. If you're just using equations, you might make it through physics 1, but nothing past that. Okay, 0.997. Velocity is 0.997 meters per second. And we kind of do a vibe check on that, like, is that the answer that we get? Yeah, okay. So if it's going like kind of a lot less than 1, but it's heavier, and then like, you know, kind of more than 1, but it's like lighter, then when they join forces, they should be going somewhere between slightly less than 1 and slightly more than 1, or, you know, about 1. Like, it's still going in the same direction. If the velocity had come out negative, then that would be an indicator that the two cars had, like, changed direction and were now going left. But see how velocity is positive, and then that kind of feels right. It feels like a weighted, and it is, in fact, a weighted average of, well, like, you're heavier and you're going slower, you're lighter and you're going faster. So on average, if you join up forces, that's how fast you guys get to go if you travel together. Okay, so that's kind of like the meaning of what we're looking like that. Okay, so here's another one. A super ball is dropped from a height. It bounces with no loss of energy and returns to its initial height. Well, that's good for it. What is the ball's change of momentum during the bounce on the floor? Well, I'm going to go with, let me just do the math and see. Okay, so if I look at the ball's going to fall down and it's going to hit the ground. This is like step 1, step 2, and then step 3. All right. Okay, so if I look at its, should I actually get a velocity and a height? Yeah, let me do that. I'll feel better. Okay, so I know mgh is 1/2 mv squared, so m doesn't matter. 1.5 times 9.81 times 2 is going to give me v squared. I just want to know how fast is it going to be when it hits the ground. I don't know that I'm going to need it, but I'm trying to get to know this problem better. Times 1.5 times 2, and I'm going to square root this thing. Okay, so it's got a velocity of 5.42. Okay. Did I say that right? Yeah, 5.424. Okay, so I know that whenever it hits the ball or hits the floor, let's just draw the picture. Okay. Let's see. So I have mv, and I'm just going to define up as positive, and I'm just going to be going straight up and down. So I'm going to drop my my vector symbols. Oops. There we go. Okay. So, and then, so its initial velocity, like as it's coming down, is 5.42 meters per second coming down. And then I'm going to say, since it doesn't lose anything with the bounce, then whenever it comes back up, it's going to be 5.42 meters per second again, right away. So I have the mass of the ball times the initial velocity plus, let's say, the impulse of external forces, in this case, hitting the Earth, equals mass of the ball times V2. And you're like, well, V1 and V2 are the same. No, they have different signs on them. Okay, this is really important. So the mass of the ball was 0.25 K. Okay, so 0.25 kilograms, negative 5.42. And then he got an impulse from the Earth. And so its final momentum is 0.25 positive 5.42. So the total change in momentum would be the total impulse that Earth put on it. So the impulse of Earth would be, 0.25 times that, and then minus a negative, so plus 0.25 times that again. So basically just double it. So 2712, 2.712. Okay, 2.712. You're like, wait, what is that actually asking? Okay, that is the change in momentum. That is the impulse that the Earth put on the ball. Okay, so the ball was like flick with a force times time on the ball of 27 meter. Wait, hold on. Why am I blanking on meters? Meters. Whoa, come back. So I have, this is in kg meters per second. That doesn't seem like a useful unit. Okay, I was just making sure I didn't lose my mind. So the units on this is kg meters per second is the impulse. Okay. Oh, which makes sense. Force, time. Okay, so I guess that makes sense. Yes, I'm down. Okay, so its change in momentum went from negative to positive. So its change in momentum, because it started out with a negative momentum and it ended up going positive, so it had a positive change of momentum of 2.71. Now, from the Earth's point of view, the opposite happened. Okay, so you can either just go, well, then clearly the Earth is negative 2.71. So another way to think of it is if we looked at the whole thing as ball plus Earth as a system, then that impulse in the center is internal, so it would need to cancel out. So the force on the ball would have to equal, the impulse of the ball on the Earth would have to equal the opposite of the impulse of the Earth on the ball, so that those, would cancel each other out. So that's another way maybe to think about it as being negative. Now here's the fun question. What was the Earth's change of velocity as a result of this collision? Obviously, not a ton. I guess I would need to know the mass of the Earth, which I don't actually know off the top of my head. Does it tell me what the mass of the Earth is, maybe? Let's see what the mass of the Earth is. Well, we'll just go see what they did. Okay. So just to make sure we've got this, we've got initial Earth, well, I guess the Earth mass is the same. Initial velocity plus the impulse from the ball equals the Earth's velocity later. Now when the Earth starts, this is just 0, because we've been doing this with respect to the ball moving up and down. So the initial velocity of the Earth is 0. The impulse is that negative 27 or 2.7 thingy, and the mass of the Earth is apparently plus. And then that 5.9, I can't spell, but you can see it, it's written right there. 5.97 times 10 to the 24 times the ending velocity. So if I've got this thingy, where did it go? 2.7 thingy, and it's negative, make it negative, and divided by 5.97, except I can't spell divided by 5.97 times 10 to the 24, then it gives me negative 4.5, and they're getting a different answer because they were rounding constantly. Negative 4.54 times 10 to the negative 25 meters per second. So yes, the Earth does change position, but you're never going to notice. So who cares? It's fine.